actually messed with the projector. I don't know. It looks awful, but I did the best I could. I know a lot about computers, but projectors baffle the crap out of me. Whatever. So a couple reminders. Lab is due on Tuesday. The lab 3 or lab 4, sorry. Lab 5 is going to be posted next week at some point in time. I will announce it, and we will go over it a little bit in class next week. Probably on Thursday is what I'm shooting for, is to have that posted. That's going to be the last one for us. I'm hoping to have the optional homework posted next week as well. So that'll just be probably some high-level state machines that I'm going to ask you to create on that optional homework. You will not have to turn it in. It will not be graded. But I will post an answer key so you can check the answers. So it's kind of like a bonus review session, I guess, for the final exam, because we'll still have a typical review session as usual. Yeah?
So, the thing on your that says 6 homework, 6 labs, not happening?
Unless we want to cram 3 more things in the next few weeks, no, not happening. I didn't think anybody was going to complain too much about that. The labs ended up being a little bit, taking a little bit more time than I anticipated, which is not a bad thing. It's just a thing that happened. So, and then I'm trying to think if there's anything else coming down the pipeline. I really don't think so. Lab review Tuesday. Next lab is out next week. Thanksgiving's coming up. That'll be a lot of fun for everybody. We do have class that week on Tuesday. It will be taped just like it always is, right? So please come if you can. If you can't, I mean, you're adults, you can make your own decisions. That's not my problem. So do what you want. Any questions about logistics stuff before I move on? Any questions? All right, cool. So today we're going to talk about circuits. So recently we've been spending a lot of time constructing these high-level state machines, like the one I put up on the board that we've seen a few times now for the rotation. And then we've also spent time constructing data paths, like we did last Tuesday. So we're going to see some more data paths today. The last piece that we need is the actual circuit that manipulates the finite state machine. So before we go into some exercises, I just wanted to kind of review a little bit what I went over in the video that I posted last week. So this was for the pulse counter, right? This was for the pulse counter. I know you probably don't have the data path for the pulse counter in front of you, but I remember it well enough that I can explain what this transition table is showing us, right? So this column here, count equals 0, that's actually coming from the data path, right? That's what's telling us whether our count variable is equal to 0 or not. You can see in a lot of cases we don't care about it. Only in this state down here do we actually care about it, right? Here's our states. What kind of encoding is this? Binary, right? It's just binary encoding. I had, 4 states, so 2 bits should cover me, right? Without too much problem. And then here's the outputs of my finite state machine. But I want you to be a little bit careful, right? The outputs here are actually going where? To the data path. They're going to the data path, right? We do have an output, like a legit output. That's specified down here. You can see equation for it. Event is the name of that output. And it's equivalent to what I'm calling Z, which is this column right here, counting to 0, right? So that is our true output. These outputs are going to the data path, which maybe I do have the data path on the next slide. I think I do, actually. Here it is. Yeah. So here's the data path. We can see here's Z, right? That's the output. A is controlling this mux. A is controlling the mux. And B is controlling the load signal into the load register. So the finite state machine is just controlling those pieces of the data path. So take a look at what that means. If we look at the first 2 rows, and in state 0, 0, that's what I've designated my reset state. So what do I do from the reset state? I read in the value of n, and I store it in the register. So what does that mean? That means my mux select bit needs to be high. That's going to select the n input. And the input to the load register also has to be high so that the register reads in that value, right? So that it reads it in. And then we see the load register is only ever activated one more time. At this point in time, we see that A is low. That's going to indicate that we're going to pull the count -1 portion of the multiplexer. So this is where we're actually performing our subtraction. We're subtracting 1 from count. And so you can see that, like we did previously, once I have this transition table specified, so you can see the next state transitions on here, same as before. I've already done that, right? That's not new. Then I can specify the equations for all of the different pieces, just like we did before. And then I can construct a circuit based off of those pieces, which we see here. It's not a bad circuit, actually. It's not a bad circuit. Just a few gates. I did take a couple of shortcuts, I guess, a little bit to reduce the number of gates. And then, so the main thing to consider is that this is one part of what we need to implement this. This is the state machine part. Okay. The other part that we need is on the next slide, the data path, right? This guy. And so when you see A and B labels on this circuit, those are directly connecting up to the A and B inputs on the data path. So are there any questions? I know this is what I already covered in the video. Are there any questions about that process? Because that's what we're doing today. We are creating these things, right? And you can probably already guess what examples we're going to use to create them. So how would the state diagram, how would the state circuit change for the other? This one I'm not sure we even need a whole lot of time to for discussion, right? Can somebody tell me, if I do the paired pulse counter, how does that change? Now, there are actually 3 options for the paired pulse counter, right? So you could choose the easiest one. The easiest one was, what? Change the data path to multiply n by 2, in which case, does that affect the state machine at all? No, the state machine doesn't change in that case. So what were the other options? The other options were to introduce more states. That would affect the state machine, clearly, right? Obviously. I would have to probably use an additional bit, at least one additional bit, if not more, to represent those new states. What was the third option that we had? Was it a second variable? Second variable. So how would that affect the state machine? What effect would that have on the state machine circuit if I added an additional variable? So it was a 1-bit register, right? Which means I would have another input that needs to be controlled by the finite state machine. So my finite state machine would gain an output. I would need another output column here to control that register. I don't think there was a mux involved, was there? Just a 1-bit register. So I just need that one additional bit of output. What about the continuous pulse counter, the one that goes back to the beginning after it gets to 0 and restarts the whole process? What do I need there? How would that change things? So I would actually just need an additional transition back to my reset state, right? So I just need one more row in this table, I think, to pull it off. So once I see that this is equal to 0, so this transition here, instead of going to this state when this is equal to 0, I would go back to the reset state whenever I see that this is equal to 0. Right? So it would just be an additional transition that I have to add to the table, which would change the circuit. It would. I'd have to redo all these equations as a result. I don't think it would change that much. If you have some time, if you have a few minutes, see if you can add that row in and figure out what those equations would be. All right. I want to do a couple examples. I've got the knob high-level state machine up on the board. We're going to start with this one today. What was the data path for this again? It was pretty straightforward, right? What was it? Data path. We did this on Tuesday. It was just a 1-bit register, right? Look at our variables. Or not 1 bit. It has to be at least 2 bits, right? For previous. All right. It has to be 2 bits. But yeah, you're right. It's just a register. Oh yeah, it was a 2-bit register. For clockwise. Thank you. Yes. Thank you. Thank you. So here's tick with the load. We've got input and output. What was coming in? What was coming out? Did we specify? Or not tick. Why did I say tick? Previous. Let's do previous first. So AB goes in, right? AB goes in. what comes out? Where does this go? To two comparators, because we need to compare against those defined values, right? So we need to compare against 1, 0 and 0, 1. Okay. Compare those values. So we would need additional comparators. Why? For A, B, for the inputs, would also need those comparators for the other values, right? I actually think we may have forgotten those on Tuesday, but that's okay. We're picking them up now. So 1, 1. Oh, my quotes look like ones. 1, oh gosh. And then the other one. 1. Right? And then this one is 0, 1. Right? Okay, and then what was the other piece that we needed? Clockwise, right? Clockwise means. It also has a load signal. What's the input to this guy? Yeah, it's just going to come from the FSM, and the output is just also probably going to go back to the finite state machine. Yeah. Did I screw up previous still? Previous is compared to 1, 0 and 0, 0. Oh, did I write down the high-level state machine wrong? I mean, it doesn't really matter, right? It doesn't matter too much as long as you get. Is this
should
right?
be, yeah, AB should be compared to 1, 1 in those cases. Because we're trying to go from like just the left button being pressed down to 2 buttons, or just the right button to 2 buttons.
Just the left button to 2 buttons. So that would be counterclockwise, right? So what I have up here is, that's correct.
But the clockwise one is going from 0 buttons being pressed down to just the right one being pressed down.
Oh, so that's also counterclockwise. You're right. So what should it be?
Yeah,
then?
it should be just the right one being pressed down to 2 buttons being pressed down.
I'm actually looking at my code here. I'm actually looking at the VHDL. Where did I?
Shouldn't AB be 1, 1 on the clockwise transition and
Shouldn't AB be 1, 1 on the clockwise transition? And yes. AB should be 1, 1 here. And then it should be 0, 1 up. That's what I did. I got them switched.
Wait.
Right? Or no, not that's not right.
No, your AB should always be 1.
That's not how I'm trying to match the code that we had. So here's what I've got for. This is for clockwise. For counterclockwise, I have 1, 0, and 1, 1. So start with 1 button pressed.
Yeah.
And we go.
And then for clockwise, the same button.
And then I've got, for clockwise, I've got 0, 0 to 0, 1, which is. That works. It works.
Yeah.
That works. I think I did have it wrong. I'm not sure. I just got the numbers swapped in my head. This is what I have in the code. This is how we coded it up. I'm just trying to match the code that we had the other day. This works. This works. So AB is 0, 1, 1 and 0, 1, and previous is 0, 0 and 1, 0. So this is good too, right? All right. Do we need anything else? Are we missing any other pieces here? So anything that's not connected is finite state machine material, right? Going either to the finite state machine or coming from the finite state machine. So both load signals are being controlled by the finite state machine. So we should give these names at this point. Previous load, clock load. Okay. This input is coming from the finite state machine, so clock in. Clockwise out. I don't know if you want to label the output. This is just the output, right? This is the definitive output at this point, the actual output from the finite state machine. And then these all need to be labeled as well.
So AB we've already got, that's our input, but these all need to be labeled too. So I might call these like AB11, AB01, previous 00, previous 10. Right. So we've applied labels to all the signals that are either going to or coming from the finite state machine. And now our task is to construct one of those tables. Let's agree on some things so that we try and come up with a similar result. The main thing we need to agree on is binary or one-hot encoding. Which you guys want? I don't care either way. Somebody shout out suggestions. Binary, let's do binary. So one fewer flip-flop, we do binary, right? And let's go ahead and assign numbers to these so that we're all working on the same ones so that we get the same result. So I'll just arbitrarily assign these, like so. Those might be horrible assignments, I don't know, but we'll find out in a little bit. So there's your state numbers. Here's your data path with everything labeled, right? Your next task is to construct that table. Talk to your neighbors. I'll be around. Elliot's back there. He'll be around, and we'll go over the answer in a little bit. Okay.
Why would slash we want to do instead of doing because clockwise is a transition to a state that immediately transitions back.
Yeah.
Why not just do a self loop on weight with slightly more complicated transitions?
I think we discussed that when we created the high-level state machine a little bit. That would have been last week, I guess. But we do need tick to be high for a single pulse. So in some ways it would complicate things because then I have to explicitly write tick to 0 all over the place.
Yeah, well, you just have to write tick equal to explicitly
on the other transition.
on the dot.
Yeah, on the other transitions. I mean,
Yeah.
I like it this way.
Yeah.
It's more personal preference for me. I would rather have more states if it simplifies my transition. But you would rather have one state transition. You may have noticed, or maybe not, it's probably possible to write a lot of these as one state.
Yeah.
But that sort of defeats the purpose of having a state.
Yeah, I mean, that's kind of what my brain tends to
Yeah.
is just
Yep. So,
gigantic transition, very complicated logic, and very complicated logic.
I understand. I think this helps kind of break it down a little bit more. Like, so you can see the pieces a little bit more clearly.
Wrong. Yeah. Okay. This, the reason why I bring it up is that this uses what actually clock tick. Like, if you need a clock tick to go back, to go there and come back. Well, it's just a self loop. That's one.
That's true. That's true. There is a little delay involved. That's actually something we're going to talk about on Tuesday.
However, that does get interesting then with keeping tick high from one and higher. If you do it where with just one loop.
It would work.
Higher next cycle, that would be like higher 95% per long cycle.
Yeah. Yeah. It's something we'll talk about. We'll talk about it on Tuesday, actually, as well. The timing piece, anyway.
Oh, previous LP. That means turn load register is register of the matrix. Yeah.
the outputs are going to be the labels to the side. And then you got one output, so you got 4 outputs. Those are actually inputs. Oh yeah.
Yeah.
Yeah, I like that. Well, with the final state machine, I really prefer to deal with single-bit signals. So the fact that we took AB in, which is a multi-bit signal, and we have these equivalencies coming out as single-bit signals makes my life easier in terms of the final state machine. That's why we have these. Yeah, that's why we have these included in our data path. So these are going to be inputs into the finite state machine, quote unquote, right? And these are going to be outputs of the finite state machine, right? As well as this will be an output as well. That's kind of part of the data path job is to take the multi-bit signals that we have and condense them into single-bit signals. The finite state machine is really work better with that. One signal is going into the data path.
Oh yeah, I guess it's just
In fact, I think we might even be able to get rid of value altogether. Might be able to simplify this a little bit. I'm tempted to do this. We're always going to previous value and comparing it with the most recent one. I'm tempted to do that. That would eliminate this column altogether. Eliminate that column. The only place you don't explicitly see that is like from clockwise back to weight. I don't know. I guess we could include that on the transcript if we really wanted to. Right? I don't think it's free. Do it that way. No, not necessarily. In fact, we saw in the example before with counters, they only change at certain times. We're about to do another example where that's also true. They only change at certain times. Actually, yeah, there's an implied loss of identity there. Let's have a conversation about this guy. It's a little tricky. So I've started to construct my state diagram. It's not complete, of course, but you know, I took a look at the. I grouped my inputs, my state, my outputs, and my next state. Actually, I could have probably filled in next state if I really wanted to. Let's see. Well, we'll take care of that as a group, right? So what am I looking for? If I'm in state 1, 0, that's my weight state, right? So I just coded up the conditions based off of these comparator signals that are coming back. Right? AB11 is true and previous 10 is true. That's our transition conditions into the let's see, into the counter state. So that's state 00. That's our next state. What do we want the rest of our outputs to be? Clock load, clock in, previous load, S0, S1. We already did those. What about these values? Do we need to do anything with these? What should these be?
Clock load should be 1, clock in should be 0.
Should clock load be 1? When do we, this is a Moore machine, right? So the outputs depend on what state we're currently in. So those outputs aren't going to get set until we're in state 00. So, we don't have to, clock load should be low. Clock in does not matter. I don't care what it is. Does not matter. Previous load, I think, I was talking about this with some other people. I think this is always happening, right? We're always reading in the previous value and storing it. Although it's not explicitly stated here on this transition, for example, that that's actually happening, or this transition for that matter, that that's actually happening. I don't think it's a bad simplification to make though, but I guess we could play it straight and assume that that's not the case. If you really want to ignore, then previous load would be 0 in this case, I guess. Right? Because we don't want to touch it. It's not on the transition anyway, so we don't want to touch it. That's basically done then, right? That's one transition down. This is the same thing. It's just going to the clockwise state. So I think the outputs are also going to be the same. And then we're just going to state 01 instead. Everybody with me so far? So we've already taken care of this transition and this transition. They're already knocked out. Now let's talk about the transitions back. So if I'm in the counter state, that's state 00, that's this state here. Let's talk about outputs. What should my outputs be? In the counter state. So clock load should be 1, because I do want to change that value. Clock in should be 0, because we're going counterclockwise, so it should be 0 that's loaded in. What about previous load? Still 0, right? Still 0 there. Still 0. And so for the next state, we'd be transitioning to 1, 0. And it'd be a similar thing for this one. If I'm in the clockwise state, I still need to load this, but now it's going to be a 1. It's still going to be a 0, and we're going to transfer back to state 1, 0. So that's 4 of the 5 transitions, and the 5th transition is actually a little bit tricky because there are a lot of possible combinations for it. Yeah.
One quick question. Shouldn't they have tick on there? Tick is also going to be an output.
Yes, tick should be on here. Shoot. I don't have to look. Yeah. Yeah, I don't have a whole lot of room here. So it should be 1 here, 1 here, 0, 0. Like that. Sorry about that. Thank you for bringing that up. Did you have a question too?
Oh yeah, you said that previous was only 1.
Well, so I said that, but then I was thinking, what if we tried to stick to this? What would that actually look like? If previous load is always 1, that's a nice simplification. And I'm okay with that simplification. But if we really want to do it like this, right? If we really want to implement it as written, then previous load is 0 so far. And the one transition that we have left to worry about is this one. But the problem with this transition is that it's basically every combination of these 4 inputs except for the 2 that we see here. And that's a lot of possible transitions to write out. I'm not sure of a concise way to do that. I don't want to sit here and write out all other do it 4 with don't care bits, you mean?
Yeah, because you just do the 4 possible options where one of the ands is false.
Yeah, I see what you're saying.
Yeah, but that's still more work than
Yeah, I can't think of a concise way to say it. I mean, I'm tempted to just say,
when
other stuff. Like, very scientific when I'm in other
other stuff in state 1, 0, then all this stuff is 0, clocking is 0. Previous load is 1, and we stay in state 1. I know that's probably not the best way to do it. Yeah. Take as an output. Take as an output to our finance state machine. So we don't have right. Clockwise is taken care of through this. Tick though does not have a register. It's a single bit, so we can actually handle it with the finite state machine. We don't need to worry about adding it into the data path necessarily. We just have the finite state machine take care of that. Yeah. Yeah. Oh, I mean, we already saw the code, right? The code is not that bad. We saw the code already last week. I think this is a little easier to. Well, so what does the code actually do? I think our code and our finite state machine might be a little bit different because in the code, this is actually true. It's actually loading this every single time, every single time. So that means this is somewhat inaccurate. We can fix that. Just do this. Previous AB, previous AB, right? Just put it everywhere. All right, cool. Problem solved. Now they match. Now they agree with one another. That changes this. So now we've got ones in this entire column all the time, always. Yep. I wish I picked up on that sooner. I wish I picked up on that last week when we created that high-level state machine. But too late now. Are there any other questions about this example before we try another one? Sure. I mean, if this were really the case, I wouldn't even include this on my transition diagram. I would mark it like this in the data path to indicate that it's always reading constantly. Okay. You guys can probably, well, actually, let's put it to a vote. Do you guys want to do another one of these, or do you want to do another data path? I don't care. Does anybody have a strong feeling one way or another? Data path, like one of those? Data path, data path, data path. Okay, let's do a data path then. Here we go. The consecutive 1 counter. Do you remember the consecutive 1 counter that we talked about last week? Let's do the data path for that guy. Let's see if I remember the consecutive 1 counter from last week. It had 2 states, is that right? How many states did it have?
Yeah, that's true. Those were waiting.
So we had 2 states, wait and count. And so if we see a 0, we're just going to hang out here, right? If we see a 1, then we stay here. And a 1 takes us from wait to count, and a 0 takes us back. I think technically there should be a reset state as well, that if it sees a 0, it takes us here, and if there's a 1, it takes us here. Do you understand why that's necessary? Because I don't know what the first bit is going to be, so I'm just going to go here first, so that I can see what the first bit is and end up in the appropriate location. So I think technically 3 states, but that's not going to affect the data path at all, I don't believe. So we had other actions. What are the actions on these transitions for the consecutive 1 counter? Do we have to do anything here? No. Here we needed to start counting, right? So we had a counter. We actually had 2 counters, I think, or we had a counter and we had like a max run or something like that. So in this case, I would start to say count plus plus, increase 1. In this case, I would continue counting, right? Count plus plus.
And then at some, well, then I would also had to do a check here to see if it was larger than my longest run. Is that correct? Or did that happen in this transition? It probably also happened. Well, no, it happened in this transition. Maybe even this one too, right? Do it in both places. Can't remember. Yeah, so we'd have to check it here. If count is greater than run, then run is count. That same thing needs to go over here, right? If count is greater than run, then run. Well, it doesn't apply when I see zeros. I'm using count to keep track of my current run. I don't remember how I did it last week, so if I need to switch variable names, somebody give me a heads up. You need to switch variable names? I just wrote count is greater than none. I did it backwards. Sorry. And then here we set count equal to 0. Here we don't need to worry about setting count equal to 0. It's already taken care of. Is there anything else that we need? Anything else that I'm missing? Yeah. What's the
on that first one you would do count plus plus.
Okay, I see what you're saying.
And then
Yeah, so this
pre-state correction algorithm will get rid of it.
yeah, this could be. You're right. Thank you. I was being overly cautious. Thank you, thank you. Simpler this way. So here's our start state. If I see a 0, I'm cool. If I see a 1, I start counting. And I continue to check to see if count is greater than run and move count over to run if it is, right? That's true. You can start on either one. Doesn't matter. Anything else? Are we good? Are we sold? Your turn. Data path. I'll give you a few minutes, and then we'll see what you come up with. Run is the output, yes. We have to remember what it is, right? It's their output.
I mean, I guess, no, you wouldn't even know if you ever watch again. Like, I don't know, resell the, like, yeah. I know.
Okay, I have some really good questions. Let's talk about this problem, see if we can figure some of them out. So, when you look at a problem and I say, give me a data path, what's the first thing you're going to look at? What's the first thing you're going to try to place in a data path? Yeah. Registers, yes. You don't have to do that, of course. I mean, you can start wherever you want. But my mind naturally tends to hone in on the registers, which are going to store our variables. So we need two registers. In this case, one for count, one for run. So here are our two registers. And so now we have to determine what's going into these things, right? So what are the possible options for count? What are the possible input options for count? 0 and count plus 1. So those are my two options, right? So here's a plus 1. What do I need to make this happen? Need a mux. Thank you. Awesome. So, and then here's a 0. There's my select bit. Perfect. Okay. What about run? Or is there anything else I need to do for count first? We good? Yeah. Isn't load just always 1 for count? I guess you could make that. So we don't need to load it over here. If we could assume that's already 0 with that.
But there's no point in having that. Yeah, it wouldn't change anything.
That's true. Yeah. You can set it to be always 1. You can write count equals 0 there, sure. Yeah. Sure. I'm okay with that. Does everybody understand? So count is basically always getting set in every single transition, so we might as well just always load it. Always. Okay. Anything else with count we need to talk about? What about run? So run, we need to talk about inputs. So the output of run is just our output, right? That's easy. This is just the output of the circuit that we want. What about the input? That's going to be, yeah, count plus 1. Okay, count plus 1. So that would be just like this. Why count plus 1?
Because you're doing the comparison on the same step as you do the increment, and otherwise your run will always get a value that's 1 less than the current value of count because the register won't update.
We talked about this actually when we wrote the code for this problem. I realized it was probably a week ago, or maybe even more. But we talked about this very problem in VHDL, right? If I have a process and I say something like this, where count is set to be count plus 1, and then I say run is set to be count. What is the value of run after this? Is it count plus 1? No, it's just count. Why? Why is that the case? Yeah, go ahead. If they update, right. These values don't update until the process is over, right? So I basically queued this operation up. Count plus 1 is something that is going to happen in the future, right? This is also going to happen in the future, but it's going to use whatever this value of count is, whatever the old value of count is, because it's going to happen simultaneously. Right? It's going to happen at the exact same time. So, so in order to make these equivalent, we need to say something like this. That would make them equivalent. That would make them equivalent. So that's what our circuit does for us as well. Yeah. Do we need anything else? We need to compare count and run, right? We need to compare count and run. Or actually, yeah, count and run. So, I'll say greater than count. Do we want the plus? Well, that's a good question. Do we want the plus 1 or not? Yeah. It's a good question. I'm trying to remember how I did it in code, actually, as a matter of fact. I think we did do the plus 1 when we wrote it out in VHDL. I actually probably still have it on my computer. I can look it up if I really wanted to, but could you do greater than equal to? So, yeah, that would work. Greater than or equal to? That would work.
I thought last time you were saying that if you use I can't remember if you use the plus 1 value instead of count, you can just say equal to.
Oh, yes. Hang on, let me think about this. If count plus 1, you're absolutely right. That's what we did say. We said if count plus 1 is equal to the run value, then we want run to be set to count plus 1. That's what is that what we said in the code? I should just look it up. Let me just pull it up.
Yeah, that would also say that
count was equal to run, then you want to set run to be count plus 1. Yeah.
Both would work.
Yeah. I mean, this is, I'm almost positive this is what we did in code. If count plus 1 is equal to run, then run is set to count plus 1, right? So, and so that changes, well, no, that's, yeah, count plus 1 is what we've got there, right? So I've got this comparator here, right? Are we good? Are we good? I know that was a little confusing. Somebody please ask me a question. I feel like there's a question out there waiting to be asked. I would like somebody to ask it. No? Okay, that's fine. Yeah. I like that question. I was waiting for somebody to ask that question. The question was, could we just take the output of this and tie it to this? Okay, well, let's reason through it. Let's think about this, right? So here's a value of count. You know, we have whatever value this is. We add 1 to it. We compare it to our run value, and if it's equal, then we're actually going to absorb that value into the run register. So I'm trying to think about how that would work in terms of our circuit. We would have, I think it seems okay. I mean, there's definitely some timing considerations that you would need to take into account here since we're feeding values from one register into another register. So you want to make sure you don't violate any setup times, hold times, stuff like that. Kind of goes without saying. I think logically, yeah, did you have
On the logic for that,
Mhm.
questioning whether that actually works. Because basically you're saying if run equals run, set run equals run.
So, because we set this to high, it's not actually going to read this value in until the next rising edge of the clock cycle, right? So this is the old value of run. We're basically saying if the old value of run is equal to the current value of count plus 1,
Set run equals to its old value.
set run equal to its, yeah, that is, hang on,
Yeah,
something.
I think it's supposed to be count is equal to run, not count plus 1.
Yeah, I think I agree with you there. Yep. Thank you. This works now, I believe. If count is equal to run, then I want run to be, greater than. Yep. I guess the only other question that I have, no, that seems all right to me. Yeah, that seems good. Yeah, that seems all right. If these are equal, then load it up. Yep. So we're basically increasing count and run at that point, right? And if they're still equal the next time around, then we're going to do the same thing over again. If they're still equal the next time around, we're going to do the same thing over again. If we ever see a 0, then what happens? Then this select bit is going to hit, right, and choose the 0, and then we're done. With that being said, this select bit should just be what? What should that select bit be? My input. Yeah, surprise. We don't even need a finite state machine for this guy. It's not even a necessity. So draw a transition table for this finite state machine, or for this data path, done. Right? Don't need one. We don't need one. This was something that I actually mentioned to you way back when we first started talking about high-level state machines. Do you remember there were a few examples where we constructed high-level state machines, but when we coded them up, there were states nowhere to be found. They just weren't necessary. It's not a necessary thing to include states. Well, sometimes the data path is good. Sometimes the data path is all you need to get the job done. That's not a bad thing. It's not a problem. No, it's actually convenient, right? This is a pretty simple circuit. Yeah.
But how would you actually reset the circuit? Something else we said about like how would you actually get run to go back to 0?
Yeah, so reset is missing. Yeah, we basically need a whole bunch of, yeah. We could have a reset.
Then maybe we get not any going in, so that your zero select can be on one.
Well, we can just label it differently.
Yeah. Well, but then you need in to be not in. So that when in is one, you select zero.
Okay, in nuts. That's fine. That's okay. Right. We need the OR date, I know. I'm being lazy. But yeah, we can easily reset it that way because as soon as count takes in the value, well, is that true though? If count takes in the value of 0, run is not going to take in the value of 0, right? So I need another multiplexer over here hooked up to run that takes in the reset signal to reset it as well. That's not a hard thing to do. It's not a hard thing to do. Just one more multiplexer. So now we've got this as one input, we've got 0 as another, and the select bit here is going to be reset. Right? So now we can reset both of these counters to 0 whenever we want and start the whole thing over again. Good. Good. Questions? Any questions? Comments? Otherwise? Here's what I would like you to do for the remaining 15 minutes. I have had a ton of questions about this lab. I would really, 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 really like you to spend the last 15 minutes working on the lab, and especially if you have not started already, you are way behind, right? So please work on the lab. I'm going to be here to answer questions. Elliot's going to be here to answer questions. If you're done with the lab, take a look at the slides on the website. There are more practice problems. You can work on those, right? Please don't leave. Please work on the lab. Use this time to your advantage. Ask me questions. Let's get this lab squared away.
So for me and Zach, we were working so we're being asked not to get them so I did that. I just said
I like having it writing. Yeah. Should we email?